All right, everybody. So what we're going to be looking at today is solids of revolution, the disk and washer methods. I think I'm calling this lecture 31.5 because this is part two of the previous lecture. All right, so let's pick up where we left off, except for one thing, which is this is just a reminder. So I've said this a few times, but I know people don't watch all of the lectures. So I'm just going to say, recall, you're not supposed to have to know these. This is, looks like it's a real recall. You're not supposed to have to know these for this class, but in practice, they sneak them in a way that was unavoidable. So I'm just going to do them here. Remember that if you ever have to do the derivative of e to the x, it's just e to the x. And if you ever have to do the antiderivative of e to the x, it's also just e to the x plus c because it's an indefinite integral there. And if they throw a constant in there, then of course for the derivative you would have the chain rule, which would make you multiply by the constant. And when you do the integral, you would undo the chain rule, which technically is substitution. But without doing substitution, you can just remember what the answer is. And so I'm writing this because you may need this on your homework, or you may not. But you get different problems every time you do the homework. So that's why I'm putting it in here. So you're not supposed to have to know this, but there was literally no way to make that problem not show up ever. So it is what it is. All right. Let's actually get into the lecture then. So what we were doing last time was we had just come up with the disk method. Okay. And so for the disk method, what we were looking at was this scenario. So you had a graph of some curve. Oops. You have a graph of some curve. You have an A, you have a B. There's a region under the curve and between the A and the B, right? So this region right here. And you rotate that around an axis. So I'm just going to say around, in this case, the x-axis, but I'm just going to say an axis. So where's your axis? In this case, it is right here. It's your axis. Axis of rotation. And we're doing this in 3 dimensions, right? So you go like that for every point on the curve in that region. And then what you end up with is, in this case, something like this. So like the top going to look like the curve. Then on the side, going to be like that. This is the worst one I've ever drawn. I don't care. Like that, something like that. And this is a volume. It's like right on the side of the iPad. That's why I can't draw it. There's something in the way. Right, so like over here, that gets rotated. Over here, that gets rotated. The curve in between gets rotated. And that's how you end up with a shape that looks like the one we've got. And we're not going to explain that very much anymore. We're going to assume we're familiar with that. And so this right here is the solid of revolution that we were talking about. I don't know why I'm doing that. I'll stop. So there you go. That's how you get a solid of revolution. And we know what the volume of that is. So what you have to do is on your original curve from the, oops, that's the wrong color. On the original curve, from the axis of rotation up to the curve, that's a radius. And we call it r of x because as you move along the x-axis, of course, the radius is changing, right? So it's not just like r equals 3. It's r equals, well, over here, it's different than here, which is different than here, which is different than here. So you need it as a function. So you find your r of x. And then the volume of the solid, right? This guy, is the integral from a to b, right? Just a to b, because that's our region, of pi r of x, parentheses, squared, dx. And that came from the fact that pi r squared is the area of a circle, right? Because this is a circle on the side here. And then the dx, when you integrate dx from a to b, that's the length. So this is an area times a length. Area, length, right? So like think over here, that's a length. And if you think on the side, that's an area. And when you multiply area and length, you get volume, and that's why this works. Okay, and this is called the disk method. So this is the disk method formula. Yeah, that's the disk method formula. And that's when the axis is parallel to the x-axis, which I think it will be for you always. What's that mean? What does that mean is that this is a horizontal axis. If it was a vertical axis, then you would just do this with y's. Everything would be in y's. Maybe we'll see one, maybe we won't. All right. So anyway, what we want to do is we want to take that disk method and just do some sample problems, okay? Just to make sure we know how this is working out. Okay, so here's the first one that the homework gave me again, and this is why I mentioned exponentials earlier, because I see exponentials here. So they say use disk method. So they tell you the method. That's nice. I mean, we've only learned one, so not that nice. To find the volume of the solid of revolution bounded by the x-axis and the graphs of, they say, f of x equals square root 2e to the 2x. Okay. X equals ln 2, x equals ln 9, rotated around the x-axis. Delete. Rotated around the x-axis. Okay, so what do we got here? So, I don't know what this curve looks like. If you want to know what the curve looks like, you always have the option of, just heading over to Wolfram Alpha or something and graphing it. So like I can do that. Wolfram. Go. Why did I do Wolfram instead of Desmos? I don't know. I think this was faster. All right. So I type it in. This is the curve. And there you go. So, I mean, it is what it is. What is it? How big is ln 9? Not very big, huh? 2 or 3? 2. Yeah, so basically we're looking at a little section of the curve that looks like this one, okay? So, it just kind of goes up. Fair enough. So, if you want to look at a graph, sorry, I have to close it because of the way this works. What is that last icon? Never seen it before. All right. So, there we go. So you got your curve, it just kind of goes up, right? And so that's, hold on, that's this. Now, what about this? X equals ln2. That's a vertical line. You can punch ln2 into a calculator, ln2, and you get that it's 0.69-ish. So, oops. So you get like 0.69-ish. That's ln2. And if you put in ln9 into a calculator, you'll find out that it's about 2.19. So like 2.19, which is approximately ln9. So you're looking at a little section of the graph like that. And then they say it's also bounded by the x-axis, which of course is the bottom. So you've got your curve, x equals ln2, x equals ln9, and then the x-axis, right? So that's the boundary of your region. So of course the region that they're talking about is in between. And then we're rotating that around the axis of rotation. And what's the axis of rotation? They say it's the x-axis, so here. So of course, when you rotate that, you're going to end up with a shape just like the ones that we've seen a few times. You know, like this side's small, this side's going to be big. What's up? What's up? Shape like that, right? When you rotate this all the way around, like so. And this side all the way around, like so. Okay, so that's what you're going to get for your solid. And of course, we should be able to figure this stuff out. So we know that our formula for the disk method is that the volume is going to be integral a to b pi, the radius squared, and then a dx. So we'll fill in what we know. So your bounds for the x-axis are obviously ln2, ln9. Your pi is just a pi. It can come out of the integral. You can multiply it where, you know, inside or outside, whatever makes you happy. R of x squared, that's where you need the radius. And on almost all of these problems, the radius it always goes from the axis up to the curve. That's always the r. Okay. But the point is that radius, like this distance, is actually just whatever that function value is, right? That's the y value right here is from this function. So the radius is actually just this function. So it's called f, but that's also the r. Okay? So you have your square root 2e to the 2x squared. That's your radius. And then a dx on the end. So this is the integral you have to do. So once you have it set up, now we should just solve it. Solve the integral. Before I solve the integral, I need to do a little bit of simplifying here. You've got to square this, right? It's r of x squared. So you square the square root, they just cancel. You get 2e to the 2x. And again, this is the type of integral that I said, technically, you're not supposed to have to know this. But they sneak one in there and it's impossible to get rid of. So you would need this formula here. It's a really easy antiderivative, right? E to the kx is e to the kx, but then 1 over k. So how are we going to get the antiderivative here? So you got your 2, and then the antiderivative of e to the 2x is 1 over 2 e to the 2x, according to our formula for the antiderivative. All right. I think you can see that the 2 and the 1/2 cancel. So you just have e to the 2x from ln2 to ln9. And you will plug these in here and here. So you're going to end up with pi e to the 2 ln9 minus pi e to the 2 ln2. Like that. And you could punch this into a calculator. I'm just going to work through it by hand here. Using the rules for logarithms, there's a rule for logarithms that say if you have a, ln, b, that you can take the a up as an exponent like that on the b, right? That's a log rule. So you can do that here and have e to the ln 9 squared, which is 81, minus pi e to the, do the same thing here, ln 2 to the 2, which of course is 4. So you have pi. Then what happens, the reason I did this was because now the e and the ln's cancel, leaving me with just the 9 squared, which is 81, and here leaving me with just the 4. So I just get 81 pi minus 4 pi. So what's 81 minus 4? Is that 77? 77 pi, I believe. A symbol, submit. All right. And that was the answer that they were looking for. Okay. Now, just a few comments here. First comment is when you set these up, if you get the wrong answer, go back and check your integral. You can make Wolfram Alpha do integrals like this just to check. So like if I go back to here, got this function, but let's delete it. Right, you can say integrate this function, I think that's what it was, from ln 2 to ln 9. There's a lot of ways to type in integrals into Wolfram Alpha that it will understand, but this is one way. There you go, 77. I forgot the pi, right? If you put the pi in front, like so, then of course you get 77 pi, and the 77 pi is what you would have to type into the computer there. So you can check your work that way. Also, while we're doing this, I just want to mention something from, you can't see what I'm looking at, from the last lecture here. So during the last lecture, I did this problem here, and then I said, this is 33.40, and then I went up to see if that made sense in terms of this area, and I was confused because I was going like, this circle's radius 3, pi 3 squared would be around 27. 27 times 7 would be a very big number, way bigger than 33. If you use the little circle, 1.2 radius, you still get a bigger number than 33. There's no way this could be 33, and I said that I thought I made a mistake. The only mistake that I made in this math from the previous lecture was I just didn't put the pi in here. That's all. So just be aware of that. So, or not, I guess it doesn't matter. All right, back to this. Okay, so that was an example of the disk method from beginning to end. Again, you can check your work on Wolfram, but you need to be able to do it, by hand reliably. Let us do one more, and then we'll be off to a different topic. Another example. So this one, they say R is the region bounded by, and I'm just going to list, or bounded by some curve. What curves? So the first curve is 7 square root 6 cosine x. They like square roots because you're going to square it anyway and make the square root go away. So why not? X equals negative pi over 2. X equals negative pi over 6. And the x-axis. So I'm just going to say we're doing a solid revolution. Rotating R, which is the region. around the x-axis. So it's still the x-axis. So this is, fundamentally the same as the previous problem. Your function here, you can graph that function, 7 square root 6 cosine x. You don't need to. Seven y equals 7 times square root, parentheses 6 cosine x. Is that what it is? That is what it is. We can look at it. We're looking from negative pi over 2 to negative pi over 6. So negative pi over 2 is about negative 1.5. So when you're looking at the graph, I can't point at this, but basically this center section here, we're just in the center section, right? Because you can see if you're on the x-axis between negative 1.5 and like negative 1/2, you're just in the left-hand part of the middle section there. So I'm not gonna, do more than that. Just gonna say we're gonna draw it. So it's something like this. We're looking at a little piece of the graph like that. And then this is negative pi over 2, and then the other endpoint is negative pi over 6. Again, it's really choppy because I have to close Notability, which I will as soon as it knows how many fingers I am touching the screen with. Okay, so, and I lost it. Awesome. So, so again, you have negative pi over 2 somewhere here, negative pi over 6 somewhere here, and in that section, it just looks like this. So your region, R as they call it, was in here. Okay, so of course, you know what to do, right? So we know that our volume, when you rotate that, is going to be an integral from a to b, pi, we can put the pi out there, r of x squared dx. We know the a and the b, seems obvious, negative pi over 2, negative pi over 6. The radius, you're measuring from the axis of rotation, which again is still the x-axis, so there to there. The radius is r of x. R is the region. How are you going to measure this distance? Of course, from the x-axis to this y value is just that function. So you come up here, that's your r. So 7, parentheses, 7 square root 6 cosine x squared. There's your integral. And I'm not going to draw the region, but, well, I guess I could. I lied. It's going to be something like that. Right? Not a great drawing, but there you go. And we have an integral to solve, and like last time, you just solve it. So solve. Don't forget to square this. Be careful here. You have to square the 7, which is 49. And then you square the square root, which cancels out the square root. So you still have 6 cosine x. Like that. So what's 49 times 6? 294. So I'm going to take the 294 out. And this is what we have. All right, so this looks like a really easy integral, doesn't it? And of course it will be, because we're going to find an antiderivative. What is the antiderivative of cosine x? Of course, the antiderivative of cosine is just sine. Easy. Then we plug in our endpoint. So you have 294 pi, parentheses, sine negative pi over 6 minus 294 pi sine negative pi over 2. Like so. So you can punch these into a calculator. Sine pi over 6 Sine negative pi over 6, I guess. Um, do we know that, right? That's just going to be 1/2, but negative. So this is negative 1/2 here. So I'm going to end up with 294 pi negative 1/2 minus 294 pi sine of negative pi over 2. Sine of pi over 2 is square root over 2, but this is negative, so it'll be negative. So negative square root 2 over 2. You work this out, and so based on the signs, you got a negative negative here. So you actually end up with positive 294 pi times the square root of 2 over 2 minus this one's negative. So 294 pi 1/2. They both have a 294 pi. So square root 2 minus 1/2. And, something like this is probably what I would type into a calculator, or sorry, type into the computer. There's not a lot of ways to simplify that. Just typing this in just to verify that this is correct, but I mean, it should be. What do we got? Square root 2 over 2 minus 1 over 2. Close the parentheses. Submit. It's wrong. What has happened? All right, let me type this in. So this is just an example of where you would want to use the computer here, right? Like I got this integral wrong, so let's find out why. So we got, well, let's just check 49 times 6 first of all. 294, so that's right. All right. So what do we know? We know that if you square this, number one, it was 2, not 4 times pi times cosine x dx. We're going to integrate this from where to where. What was it? It was negative pi over 2 to negative pi over 6. (147 pi). Oh, okay. I'm an idiot. What am I doing here? In my head, I treated this like this was pi over 4. This is 90 degrees. Sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. This was just negative 1. So then we're here. This is just, this one's wrong. That was just positive 1. And then this is just 1 minus 1/2. So that's just 294 times pi times a half. And then you do 294 times a half, and you get 147 pi. Okay, yeah. Helps if you can do basic trigonometry, which apparently I cannot. Okay, so, and it is gone again. Everything I just did just got erased. So annoying. All right. That was a 1. That was a 1. That's a 1. 1, 1, 1, 147 pi. Okay. I really hate when it gets bogged down like that. Okay, so that's it for the disk method, okay? That you're going to have a lot of problems just like that. Okay, so let me see another one. So these are easy peasy. Looking for a washer method. Not seeing it. Yeah, there we go. Okay, cool. So now what we want to talk about is the washer method. So new topic, washer method. All right. So this is pretty much the same method actually. So the difference is this. So what you're going to have as a new situation is two different curves. So you've got like a curve like let's say like this. I know that's just a straight line, but that's fine. And then let's say you got another curve like doesn't really matter like this. I'm just trying to. I drew that one. See, not as not quite straight. Okay, so that way they're not quite straight. So the top curve, let's say, is y equals f of x, and then you got a bottom curve y equals g of x, right? And then you still got a b on the x-axis, and then this is your region here. And what we want to do is we want to rotate that around the x-axis, just like we did before. So we're measuring a distance from here up to here, but also we're measuring a distance from here up to here because there's two different curves. And anyway, what we're going to do is we're going to rotate this entire thing around the x-axis. Again, we're just using the x-axis for now, axis. And when you do that, like what would the shape be? Hopefully you can see that what happened is if you rotated that shape is that you'd end up with like, okay, well, I guess you wouldn't see it from the outside. Um, so you end up with something like this if you were to rotate a section like this, where your volume here is the part that I've shaded, and the inside, right, is just an empty, it's just empty in the middle, right? So empty in the center, right? There's a hole in the middle, right? Because there's no region down here. So if you rotate just this all the way down to like down here, right? And that went all the way around, you still had nothing in this center section. So this whole middle section is empty. It's just a hole in it. Okay. And we call this method the washer method because if you take one little slice here of the curve, like if you take one little rectangle like that and you rotate just that rectangle around, of course, that one little rectangle rotated around the axis will look like this. Um, might be very thin. And if you look at that straight on, it would just look like this, right? Which looks like a washer. If you take one little slice of this, um, one little slice of this, as opposed to the previous method where there was no hole in the center, right? So if you did this with with no hole in the center, then you get a picture, well, like this, right? And this right here is a circle we're looking at from an angle. So if you looked at it straight on, it would just look like that, which is a disc. So disc, washer. And those are why we call the methods the disc method and the washer method. Um, all right, so that's the setup, is we're trying to do this. And it turns out that it's not really that hard to do, because if you think about it, this is no different than, I think, 2 or 3 lectures ago when we did area between curves, right? Um, if there was no bottom curve here, right? and you calculated this volume, then all of this would be filled in, right? And that would be the disk method. Right? If you did this, that would be the disk method. And then if you add a second curve, with a different color, like that, and you did the disk method with that green region, that would be the area inside here. And so if you cut out the green area from the orange area, then you would be left with what you actually wanted. So you cut this out, cut out the center, and then you will be left with this area, which is the area that you wanted. So it's the same idea. So you remember this. So you should recall for area between curves, recall area between curves was given by like an integral f of x minus g of x. That's all, where f of x is the top curve and g of x are the top and bottom curves, right? So you remember that, right? So how does that apply to the washer method? Well, it's exactly the same idea where you can think of it as just doing the disk method twice and then subtracting. So the picture, move thing that's in my way. So the picture, you've got a curve like this on top. And it's the same picture that I just drew, but I'm drawing it again. You've got a curve on the bottom called g of x. Now your region is between these. You still have your axis. So the axis is down here. And this time you've got two radii. You've got one radius to the top curve and one radius to the bottom curve, right? And so there's different conventions for this. Usually what I do is I call the top one big R and I call the bottom one little r, like that. And then your volume is going to be this. Volume, no surprise. So you could write it in two integrals, pi big R squared dx. That's the disk method for just the top curve. But we want to find the area between them, so we could subtract a to b pi little r squared. Or the way they actually write it is this. Washer method. Volume equals, they put them in one integral is all they do. So they say, they put the pi on the outside typically, and then they'll say r of x, big R of x squared minus little r of x squared dx. Okay, so that was a lot of work, 10 minutes or something just to get this, but it's exactly the same as the previous problems. The only thing is now you've got a top curve and a bottom curve to worry about, which gives you two different radii when you measure them to the axis. All right, easiest way to do this is to do a problem. So I've noticed that the first thing I see here doesn't actually have us perform the washer method. I don't know if that's typical or not, but they say consider the region bounded by, and again, a bunch of graphs. So they have f of x equals 0.1 e to the 0.5 x. G of x equals 9 over square root x plus 3. X equals 0, x equals 5. We want to rotate that around the x-axis and find the volume. So rotate the region around the x-axis. And find the resulting volume of the solid. And it's a solid of revolution still. All right, so you got to know which curve is on top. In order to know that, you could graph them. We're looking in the between x equals 0 and x equals 5. You do have to know which one's on top in order to do this. So Desmos may be a better place to do that. Graphing calculator. So what do we got? We have y equals, our top curve was 0.1. Give me an e to the 0.5x. Where's the exponent? All right, there we go. And then the other one is 9 divided by square root x plus 3. X plus 3. Okay, and we're looking between 2 and 5, they said. So between 2 and 5, you should be able to see, right? We got 2 right here, and the blue curve's on top, and over to 5, and the blue curve's still on top. So the blue curve's always on top. So it's this one right here, 9 over x plus 3. That's the one that's always on top. So let me look at that one more time. So blue curve is like down and to the right. Okay. So what we got was the blue curve was down and to the right. And that was the g of x. And then the other one was up and to the left, and its exponential was like that. That was f of x. But then like 2 and 5 were like that. So we're looking at a region something like this. All right. So that's what our picture looks like. Again, I have to close it. I think it will save it this time though, and I won't have to redraw what I just drew. Yeah. Okay. So this is the region we're talking about. And so we can draw our little radii. Again, your axis, you got to know your axis, but it's just here. And then your little r is there. And then the big R is there. So the big R is actually going to be g in this case. So your integral is going to be the integral from a to b. Put the pi on the outside. We got big R squared minus little r squared dx. So for us, our volume, a and b are 2 and 5. We can see that. The big R is g. So where's g? G is the 9 over square root x plus 3 squared minus little r. Little r is f, which was the exponential 0.1 e to the 0.5x squared dx. And if you look at what they want, they're not asking us to do this integral in this problem. They only want to know which integral was correct. So like if you square this, right, this is squared. So square the top, you get 81. Square the bottom, you get x plus 3 minus. And then over here, if you square this, you would have to square the 0.1, which is 0.01. And then e to the 0.5x, when you raise that power to a power, you multiply the power. So 2 times 0.5 is 1. So it just works out like this. And then this one right here, this is the integral. They're just actually picking this off a multiple choice list. So choose this in the multiple choice section. They did not ask us to do this integral, which is good because this is kind of, we're not supposed to know how to do this either. That's a natural log. All right. Let's see, based on the time, I can do one more. See if I can find one that's different. Maybe there aren't any different ones. Yeah, okay, good. Um, yes, excellent. This is a good one. This is a good one. Okay, so again, volume of solid of revolution. They're all volumes of solids of revolution. They ask them in different ways. Formed by rotating, I'll say R around, what are the curves? That's what we need to know. The region around R, bounded by above, they tell us above and below, that's nice. Above by f of x equals x plus 2. Below by g of x equals 5 over x. Over the interval 2 to 6. And then, like always, they say we're rotating around the x-axis. The axis is x-axis. Okay, and we want to find this volume. Okay, this is really nice though, because they told us the functions and they told us top and bottom. And since they told us top and bottom, we don't have to go to a computer to figure that out, or graph them by hand. We've got bounded above by f of x equals x plus 2. Well, that's just a straight line. Well, you know, straight as I can draw it. Right? And then on bottom, they tell you you've got the curve 5 over x. 5 over x looks like this. Not like that. It changed the curve on me. Like that. I don't know why I called them y instead of f and g there, but I did. And then they say 2 to 6, and 2 must be somewhere over here, and 6 must be somewhere over here. All right, and so the region is in there. Now, how do I know that the 2 is here and not over here? Because if the 2 was over here, then this wouldn't be on top anymore, right? And they told us it was. So, I mean, you could figure it out as well, but in order for this one to be on top, the 2 had to be somewhere in here. So, okay, I drew the region, and we want to set up the integral. Now, again, you just got to think about the axis and the radii. Axis, little r, big R. So your integral for this volume, a to b, pi, don't forget the pi, big R squared minus little r squared dx. Sorry, I didn't put the of x's because I was being lazy. So for us, what do we got? We got pi integral. Bounds are obviously 2 and 6, right, on the x-axis. Your big R is the top curve. Top curve is x plus 2. Minus the bottom curve. Bottom curve is 5 over x dx. So does that make sense for the volume? So there's our integral. Let's call it v. Should make sense. Before you try to do this integral, you need to like work this out. A little bit of algebra here. Multiply this out, FOIL it. You get x squared plus 4x plus 4. Over here, you have to square this. That's going to be 5 over, no, it's not going to be 25. It's going to be 25 over x squared. Now I want to do this integral, but before I do, I want to rewrite it. So I've got x squared plus 4x plus 4 minus 25 over x squared, but we want this written differently, right? We have to integrate this. So how about writing it 25x to the negative 2, right? That's how we want it for the power rule. So rewrite this, make it easier on yourself. Now integrate. Just keep this pi on the outside of everything. So antiderivatives. So power rule, power rule, power rule. So power rule for x squared, x cubed over 3, right? Add 1 to the power, 4x. That's going to be 4x squared over 2. Again, add 1 to the power, divide by the power. 4 will go to 4x. Here, if you add 1 to the power, negative 2 plus 1 is negative 1. So the power is going to go to negative 1, and then we're going to divide by negative 1. Then 2 to 6. All right. Before I plug in my limits of integration here, I just want to simplify this a little bit. Negative, negative means this is a positive. The 25 is on top. X to the negative 1 is an x in the denominator. So that's how we could write it. And we're going from 2 to 6. So you have to plug a 6 in here. So you're going to get pi 6 cubed over 3, 4 times 6 squared over 2, plus 4 times 6, plus 25 over 6, minus, and then you plug a 2 in. Oh, this has got a pi 2. 2 cubed over 3 plus 4 times 2 squared over 2 plus 4 times 2 plus 25 over 2. Yikes. And so you got to work this out. So luckily today I did grab a calculator that does fractions. So I got 6 to the 3 over 3, that's 72, plus 4 times 36 over 2. So I'm at 144, plus 4 times 6. So I'm at 168, plus 25 over 6, which gives me fractions. So this works out to 1033 over 6, nice round number. And then the second one, what do we got? We have, so I'm doing this, 8 over 3 to start with, 8 over 3 plus 4 times 4 over 2, 32 over 3. Oh, sorry, temporarily sidetracked here. Plus 8 plus 25 over 2, 187 over 6. We're subtracting these, so pi, and then I'm going to subtract this minus this. 1033 over 6 minus 187 over 6. My calculator just messed up. 1033 over 6 minus 187 over 6, 141. It's a good sign that all my fractions managed to cancel out. It give me 141. I'll type that in and hope for the best. Oh, we missed the pi. Okay, that's correct. Okay, so that is how these go. So I think that's it for this homework. The key, again, is for the washer method, you have 2 radii. That's about it. Okay, so that's it for now. I'll talk to you guys later. We have more stuff to do, but this should get you through the homework.